some analysis of yesterday's contest, and then, as usual, I selected one of the problems from which I would like to continue talking about on some particular subject. Today, this will be the problem about intelligence quotient. So it will be an IQ problem. And we'll talk a bit more about how to solve this problem and similar problems. But this will be at the second part. I guess we can start again. So we have the 11 problems, and this time there were roughly five easier problems, and from there it was just way harder. So this was a bit different type of a contest. And first of all, there was this problem about bullet stuff, and as usual, as I see, everyone who attempted this problem managed to solve this problem, so it's no point in analyzing it. On the other hand, there was also a bit more technical problem about cross spider, in which you had to check for a given endpoint whether are they all coplanar or not. Do they all lie on the same plane or not? And this is actually, well, there's a number of solutions here, and it really depends on how you solve geometric problems. You can use cross product and other similar stuff here. So since there are many different techniques, and I'm not sure what techniques you actually use for solving such geometric problems, I also wouldn't like to get into details here. There's a number of solutions. This is a more classical problem. And then the next one, the next easiest one, was the problem. It was much more interesting one about afternoon tea. Yeah, this is a nice problem, since you can either just keep writing a lot of formulas, as I went along with your teams yesterday just to see how you try to compete and try to solve these problems. I saw that you like people with lots of formulas, like related to this afternoon tea. But on the other hand, if you like attempt, make a very smart attempt, you can have a very simple solution for this problem. So in this problem, there is this H letters denoted T, that we add T to that we add T to the teacup, and then is that we add milk to the teacup, and in each, first we start with a teacup that is filled half tea, half milk, and in each step we drink half of the teacup, and then we either add H, which is tea, or M, which is milk, and we have N rounds, which are given as a single word. So for instance, this word H, M, H, H, M denotes the situation when we drink half of the teacup, add tea, drink half of the teacup, add milk, and then so on, add tea, and add milk. And we don't really drink the last teacup. So the last pouring here, the last liquid that we add is like, we don't really care about it because we don't drink it afterwards. It's not important. And the question is, what do we drink more? Whether we drink more tea or whether we drink more milk? Yeah? We drink more tea or milk? And note that we don't have to say how much tea, what's the amount of, how much tea, how much milk we actually drink. We just care whether we drink, which of these two we drink more. And as a nice attempt to this problem and similar problems is to formulate a different question. Not to ask which of these two liquids we drink more, but the question is how much do we ask, first of all, how much of these two do we actually add to the teacup, and what remains in the teacup? Because what remains we remove. So initially we have half of teacup of milk, of tea, and half of teacup of milk. And afterwards, we perform the number of H letters in this string is the number of halves of teacups of tea that we add. So the amount of, maybe I'll do it this way. So the amount of tea is that we pour to the cup eventually is 1/2 plus the 1/2 times the number of letters H in the initial string S, and to the number and for the milk we have 1/2 initially plus 1/2 times the number of milk pourings inside. So this is the amount we actually add during the whole process. After we remove this last pouring, which we don't care, and what remains is just 1/2 of teacup of something. There are some liquids inside this teacup. Some part of this teacup is milk, and some part of this teacup is tea. And from this, what we see is, well, first of all, there are 3 cases in the solution. Case 1 is the special case, and we might have encountered it during the solution, is n equal to 1. When we have just 1, when we just add some liquid once, it actually means that we don't add anything because we don't care about the last adding. So we don't add anything. So we just drink half of the teacup and that's all we drink. So here the answer is HM, which means that we drink the same amount of milk and tea. Okay, so this was just one of the 3 cases. The other case is when the number of letters H in the string is different than the number of letters M in the string, the number of occurrences of the letter M. So this means that we add that one of these 2 numbers is at least by 1/2 greater than the other of these 2 numbers. However, what remains is at most 1/2. So, like this half of the liquid that we add, this like half more that we add, is more important than what really remains afterwards, because in the end it remains 1/2 of the teacup. And there's one nice observation that we can make actually, that this 1/2 of the teacup contains at least a bit of tea and at least a bit of milk. Because like you cannot really, like drinking all the time, you always just divide the amount of tea and milk by 2 and then there's not something. So this half of teacup contains at least a bit of milk and at least a bit of tea. At least a bit of milk, H and of M. So this concludes that if one of these 2 numbers is greater, then actually we already know that we have, during the whole process, we managed to drink more of this kind of liquid, because like there's just at least 1/2 more, and from this remaining, you cannot really beat this type of liquid. So then, if the first one is greater than the result is H, we drink more tea, else the result is M, we drink more milk. Okay, so this was the second case. And the third case is when these 2 numbers are equal, equals the number of milk. So then it's not that easy to really say which of these 2 we drink more. However, we can try to see what is the last term that we actually perform. So then these 2 numbers are equal. So the only thing that is important is what remains. Yeah? If there remains more milk, then we drink more tea. If there remains more tea, then we drink more milk. And what we actually do here is we take a look at the last but one term. So the next to last one. So we remove the last adding of the liquid, and then we take a look at this one. So this means that at the very last moment, we add at least half of the half of the cup we add tea, and afterwards we have, and well, so assume that there's S, this several parts, then we have tea, and there is this like last one that we already removed. So So this means that at the very last moment, the teacup contains 1/2 of the teacup is tea, and there is something that is resulting from all the stuff that was like previously, but it says that this the remaining part has at least a bit of tea again, plus some epsilon of tea, or some epsilon greater than 0. So this means that if the last pouring is like that, and then what we drink just half of it, so still the amount of tea in this teacup is greater at the very end, which means that there's more tea, so we drink more tea, because more tea drinks. So in the third case, we just compare. If the next to last, or we believe the last because we already removed this last letter. If the last letter of S is H, then the result is milk, else the result is milk. So this is the complete solution. We have these three cases. Actually, you don't have to do it this smart way, because also alternatively you could just sum up some fractions and just try to manipulate them and try not to get like a lot like. So yeah, this was quite a tricky problem, but a nice combination of things. Okay, so maybe let's proceed to something else. Already. But yeah, so most of the teams managed to solve this problem. Now we're getting to something that is more difficult. There was this task about laundry. This was a very interesting problem with a 3D solution. And you just have to have the right 3D solution. This is a case that, just check it. No. So, 11 teams managed to solve this problem. So what we have here is that we have n friends and k pins close. And both of these two numbers are at most 1 million, so they are large. And there's quite a bit complicated story that each of the friends collects his laundry for 1 day, for a number of days. So di is the number of days the friend collects laundry. And this actually means that he collects collects shirts and socks. So it means that he has 2 DI socks afterwards and DI shirts. And for each sock you have just 1 clothespin because we want to dry the laundry. So here we have 2 DI pins, I'll just call them pins, and here we have 3 DI pins because each shirt requires 3 pins to dry. And we have so we have K not clothespins but K colors of clothespins. And of each color of clothespins we have the number, we have Li, which is the number of pins of color I. And what we have to do, we have to, for each of the friends, so for each of these guys, we either choose 1 color and we can assign him 5. So we can, for a friend, what we can do, we pick either 1 color and we size at least 5 DI, so for which we have at least 5 DI bits, and then we assign this color and we remove this color, and this friend has already been processed. Or we pick 2 colors, 1 at least 5 DI, 3 DI, the other at least 2 DI, and we remove both colors from the set of available colors. And we want to find out whether or not we can assign colors to the friends so that these conditions are satisfied. And if we can, we need to find the smallest number of colors that we need to solve this problem. There are problems that look like problems that require a greedy solution, and this is one of such problems. And indeed, it requires a greedy solution, but it's good to know what greedy solution works and why it actually works. So we see that to minimize the number of used colors, it is clearly better, or clearly it's like a conjecture. It's better to take this color of at least. So for the front eye, it's better to find a color which can satisfy his first requirement, so provide 5 DI pins. It is always better, and if we cannot do that, then we have to try to choose select the second option. So the solution is as follows: we consider friends in the order of non-increasing DI. So consider DI in non-increasing order, so which means from the largest to the smallest, basically, and for each of them, and we store a set of all available colors with the number of pins in each color, so we have a set C, which is the set of colors.
You have, for example, 10 DI pins for one color. You can give 5 to.
No, we remove the color.
Ah.
Yeah, the color just vanishes. So we have to find one color and just remove this color. And here also remove the color. Because it says in the problem statement that I need to the same color can be used for 2 different friends. And also can remove color. So we have the set C that stores the sizes of these colors, so it actually stores a set of numbers Li and set. And what we actually do is for each of the DIs, we first check if C contains a number, an element, which is at least 5 DI, then we just remove the smallest such element from C. Remove the smallest. Of course, we want to take the smallest one because like then we lose the smallest possible, the smallest of such elements. And otherwise, like do the same first for 3 DI and secondly for 2 DI. Do the same thing for 2 DI and 3 DI. And we keep repeating this until either we run out of pins and then we say no, or we've satisfied all the friends and then the result is the number of elements that we collected from C. So here C can be implemented as a set of elements. Yes?
Considering you are doing the non-increasing order,
Yes.
isn't it the same to remove any of the elements that contain at least 5 DI?
Yes. And here it is important to use the smallest one. Here it's just not yes. But yeah, here is okay, so since C is implemented as a set like data structure, we can easily extract the first element that is at least 5 DI or at least 2 DI or 3 DI. And the basic question, as in greedy algorithms, is why it works. Well, there's a nice argument that it just passes the test cases, so it should work. However, maybe we can try to argue a bit more about this, why it actually works. And well, how you normally try to prove such a solution is correct it's not a bad idea to try to like make a short proof of such a solution just for yourself before you start implementing it. At least it gets more complicated than this. For this kind of solution, you can just try to submit it. However, you have to have some idea of why. So why this solution actually should work. So it is a nice idea to analyze it this way. Consider like our algorithm and let ALG, our algorithm, be the set of the matching of the colors of clothespins to the particular persons, to the particular friends. So this is actually our solution. The solution that we get, it might not be a complete solution, so there might be just elements that are not matched, like friends who are not matched, and let OPT be the best solution that exists. This is a hypothetical solution, so it's like we know that there exists the best solution, so we don't know which is this, but we know that it exists. And we want to find out, well, what do we want to actually prove? If we prove that this solution is the same as this solution, then okay, like this is for some particular input data. If we prove that ALG is equal to opt, then we are done. But it might not be the case. If OPT is not a complete solution, so there are friends who don't have their colors of clothespins, then actually we don't care what is ALG, because OPT is the optimal solution, so we cannot get better than that. And if for this guy the answer is no, then certainly we won't get better than that. So if OPT is not full, like complete, what we actually do, like, we are also done, because whatever are the elements of ALG, we know that OPT is, we know that the answer is no. So the only interesting question is, what if OPT is full? Yes? If OPT is full. And ALG is not equal to OPT. What happens in this case? In this case, we actually want to compare these two solutions. So we can try to consider all the people, all the friends which appear in this problem, and we consider them in the order as they appear in the solution ALG. And we want to find the first person for which there is a different matching of pins in opt and in ALG. So because they are different, so let DI be the first position where this solution is different. And now what we want to do is we want to see what OPT does with this person, see what ALG does with this person, and then correct OPT so that it works exactly the same as ALG. And then repeating this process, we get that after several transformations, we get that OPT will be equal to ALG. So just a few cases, maybe I won't write everything here, just briefly, very briefly. If DI is not, so let DI be the first person by the giver. So what can actually happen? There can be several cases. For instance, if DI is matched in OPT with so we have several cases. So first case is that in what happens in OPT and what happens this short table. What happens in OPT and what happens in ALG? If in OPT DI we have this matching of 5 DI, yes, so we find a color that contains at least 5 DI pins and just assign it. And here also is 5 DI. Then what we can actually do, we can take, if this is a different color, we can certainly take the smallest color that is at least 5 DI, this is what ALG does, and just exchange these two and we are done. But the same if this is 2 DI and 3 DI, and here is 2 DI and 3di. And what is more interesting is what happens if OPT does this with 2di and 3di, and ALG does this with 5di. What we can actually do is we can take these two and exchange these two for this one color with 5di. And if there was another color here, if there was some other person this color, we can exchange this guy into these two that were selected in OPT. So here is just some color A, color B, and color C. And what we do is we exchange these two into this color, and if there was something in this color selected in OPT, we select A and B. And there are just several cases of that. I won't be going into because there are a few more cases here. So what we basically do is see that in each case where these two solutions differ, we can somehow manipulate the solution OPT so that it becomes so that the matching on the person DI is the same in both solutions, and we just need to find out whether these we need to show that these two this matching can be corrected without making the solution worse. And after considering a number of cases, we see that at each point we could make it better, and since the order of the people is not limited.
But yes. When does it happen that OPT has, for example, 2di and 3di doesn't have 5du and 5dj, while ALG has 5di, like 2du, 3du, and 2dj and 3dj? Why can't it happen that in an optimal solution, I would prefer for a higher DI, choose to put the source and the shards in different colors, and then next to that.
This case.
This case, but then in the following cases, next to that.
I don't really care right now what is in the following cases. I want to just make a local purge. So maybe I'll just explain this very case in some more detail. So this solution OPT has 2di's in color A, 3di's in color B, and in the color C we don't know. We might use it, we might not use it. And this solution has 5di's in color C, and colors A and B, we don't know what it does actually. But we don't care. So what we do here is that if C is free, so there is no friend assigned to this color, we just take these two, throw away these two colors and put this one color, so we have a better solution, so this is not possible. On the other hand, if C is not free, so C contains, well, what it can contain? It can contain either some 2di or some 2dj or some 3dj or some 5dj. It can contain none of these. So what do we actually do? We still put both of these two into the color scheme. And then what we see is that if this contains 5dj and we consider gi's from the order of the greatest to the smallest, then I know that I can, for instance, so then the solution is like that. Then the new matching is that C contains 5di and A contains 2dj and B contains 3dj. So this is the new matching in this case. Because we can just substitute, and since dj is not greater than we can make the substitution. Afterwards, then similarly, if this contained if C contained 2dj, and we know that dj is smaller than di, then we can just put into C we can put 5di, and into A we can put 2dj. And here we have a better solution. And similarly, in this case, in the third case, C contains 5di, and B contains 3dj. So in each case we can substitute, and we make a very local substitution. We don't care what happens next. We just see that we didn't really break down anything that we have already matched. So all the elements, all the first elements in which ALG and OPT had the same result still have the same result. And on this very next element, we see that we can make a local correction. Hope this more or less answers the question. And then we can just consider there's also a few more cases that we could consider here. After considering all cases, we see that we can correct OPT so that it is like it is the same on the person DI as ALG. So that's yeah, but still if you aren't really totally sure of having a certain problem and you keep fighting with it, it's maybe just sometimes the case just to try to submit something and see if it works. But here you could have actually made that. And next, there is a problem about buffers, for which I was actually a bit surprised that it was not really popular among the teams to solve. I'm not sure what is the reason actually for the problem about buffers. Maybe you don't like buffers. No idea. Because I consider it not as difficult as some other problems that you really try to tackle. Okay, maybe I will just, like, in the course of explaining this problem, maybe we will find out what is the reason for that. So in the problem about buffers, we have buffers in n holes. And with these holes are the positions from x1, xi, xn. These are the positions of the buffers along the line. And these positions are actually like the distances from the hole number 0 from the left end of the line of holes. Positions of holes, like distances from one to the other. And what happens is that some evil the industrially keeps putting CD players along the line, and if we have several of these positions, and there is the CD player put at some position, then it has range L, which means that both here and here on the distance L, all the holes that are in this interval get like the poor gophers cannot fall asleep because of the CD, so these gophers like get unhappy. So this is this position, this position, this position, this position. And we have a dynamic problem of checking how many gophers are actually threatened by these CD players. So we have a number of CD players that are located. All of these CD players, it is very important, have the same range. So L is common for all CD players. L common for all CD players. This is important, so I write it down. And we have just the number of operations. Initially, these CD players are located along the line as specified in the input, and then we just make local operations. We take one CD player from a position and put it at some other position. And we just want to simulate this whole process. So this problem is actually about the selection of data structures. And that's actually all in this problem. All is in this problem. So first of all, we need to have a data structure that so we want to see how to store the gopher positions and how the holes and how to store the positions of CD players. Since CD players keep are inserted, deleted, so we just take one position and put it at some other position and so on, there must be quite a flexible data structure for CD players. This is a set-like data structure, a balanced model. Yes, so CD players will be contained in some sets. Yeah, that's so a balanced. On the other hand, the holes are very static. We don't have to do anything. We don't have to like change the positions of holes. So for the holes, just a sorted array is just fine. Sorted array of holes. And the most important thing is how do we actually compute the result? How do we compute how many holes are threatened by the CD players? Just one number, which we keep storing throughout the algorithm. So we store the number and just the result. We just and we can note that everything that happens in this problem can be illustrated by two operations, either insert and CD player or we delete it. Because like first putting these CD players in some initial positions, you can just put them one by one, and then moving a CD player from one position to another, you can just take the CD player, so delete it once and then insert it once. So we need to know how to do insertions and deletions of CD players. Okay, so how do we actually do it? So consider, for instance, insertion of a CD player. So there was this previous CD, the CD player. So this was this previous CD player, the next CD player, and now I want to insert, for instance, here the CD player. Note that all of them are the same intervals because they have the same values. So if this is the guy that I am inserting, so what I have to do, I have to take, because I store all of these guys in a set-like data structure, so I need to find out which is the next one and the previous one in this data structure. From these two, I can compute which is the interval that was not covered by any CD player but is covered right now. Because like from these two, I know how much this new CD player is, how many positions it is to the left from its right neighbor. From here, I know how many positions to the right from its left neighbor. So I just can compute this interval in constant time, knowing the position of this CD player and this CD player. And what I know, I want to add all the holes that appear in this interval. I want to add all of them to the result. So if I just do binary search and I locate how many of these are there, just I find that. So on this interval of newly covered holes, I find the first hole starting in this interval, the last hole which is still within this interval. I find it using binary search of the array of holes, and then I just update the result. And same for deletion. If I have a number of intervals, so I have this CD player, and then this CD player, and I want to delete this guy. What I have to do, again I check which is the previous one and which is the next one in the set data structure, and then from this I need to compute which is the interval of position that was covered only by this CD player. Again, we have to note that the lengths of these intervals are all the same. This is very important. So I just find this interval of positions. Again, I need to check how many holes are there in this interval, and then decrease n by the number of such holes. So here I increase the number, and here I decrease. And that's basically it. So that's binary search plus set manipulation. That's all. So I'm not sure. Did you like the problem or? Well, it's quite difficult to ask people who didn't try to solve it why they didn't try to solve it. But
what would you do if L wasn't common to our CD?
I would be happy. It is very important that happens. Yes?
Use a solution based on the idea of the area of union or for example, that doesn't take into consideration the size of the user.
Oh, you have a general solution that works for any app?
Yes.
Then
Even if they have different zones. We use a second tree for we don't have any holes. So you consider each hole as one unit in a line. And each time you add a CD player, you consider it's an interval that will start a rectangle that goes on time. When you remove the CD player, it's the end of that rectangle.
Ah, so you do it somewhat offline. Yes. Ah. And then for each hole. Ah, I see. Very smart. Okay, so you can just,
We also have a similar solution, but that is not applied and also works for any bank, also based on the second degree.
so maybe the reason is that you all try to solve like a more difficult problem instead of this very simple one that you try to propose. But it's interesting that you can solve. Well, we didn't really think about what the color is different. It was supposed to be not a very difficult problem for just playing with sets and sorted arrays. This was the mechanism. Okay, so this is interesting to hear actually. Okay. And this is when we leave the area of the problems that were easy or like medium, and now we are getting to really harder ones. And yes, I'm happy to see that 3 of them you managed to solve. So maybe let's start with the least pleasant one. This was the one about arithmetic rectangle. Maybe so many people try to attempt it because it starts with the letter A, so it's the first one, the first problem. It's something that's like if you don't have a nice idea of implementation, then the implementation of this problem can be a bit of pain. So the problem statement is very easy. We need to find the arithmetic grid. We are given some grid of integers. There was this one a bit misleading part that we can have 10,000 of test cases. Each of the test cases can be at most 3,000 by 3,000. So this gives like enormous input data. However, you can assume that there is at most the total size of input data is at most 20 megabytes. So this is integer. So we get this arithmetic grid. So we have a grid which is composed of numbers, and I want to find the largest area arithmetic rectangle here. And what is an arithmetic rectangle? You have to have arithmetic progressions both on all of the rows and arithmetic progressions on all the columns. This is what we have. And you want to find the rectangle of the largest area. And the model solution reduces the problem to some other very common problem. At least it's very common in Poland, but I hope here also. There's some nice problem where we also have to find the rectangle with the largest area that satisfies the condition that we have only numbers zeros and ones, and you have to find the rectangle with the largest area containing only ones. So this is like the basic problem that we want to reduce our problem to. Is to find, so we are also given a grid, 0, 1 grid, so we have only zeros and ones. Find the largest area, one rectangle. So the largest rectangle that contains only ones. Are you somewhat familiar with that problem? Some of you? Maybe a short one. Okay, so this is okay. So, like, if I see a problem to find a maximum area rectangle doing something, I always try to reduce it to this problem. And here it turns out that I can reduce it. But it's quite smart how to do this. First, you have just two cases. So we need to somehow separately consider rectangles which have very small width or height. So let W times H be the size of the resulting rectangle. The one that we really want to find. So first of all, we can have that W equals 1 or symmetrically H equals 1. Which this means that the rectangle that we are looking for is just a single strip. Well, for a single strip, it is extremely simple to find, because then if it is, for instance, a horizontal strip, then we don't really care about the columns because all the columns just contain a single element, so they are always arithmetic sequences. And if we have this strip, if we have any strip of the original grid, we can just find which is the longest arithmetic progression starting from the beginning. We can cut it at this position, and from this element, the next element we need to find which is the longest arithmetic progression. And we just cut each initial grid into arithmetic progressions, and we take the longest out of all these, and then we do exactly the same for columns. So this is quite easy to solve it in linear time. Just very simple problem. And also quite a simple problem is when w equals 2 or h equals 2. Then what we have is, for each, I could give this just an exercise for you. So if I have any two consecutive rows of the board, I can cut each of those rows into arithmetic progressions, like maximum arithmetic progressions, and then I have a similar stuff below. And then what I need to find, still every column, if I extract any rectangle any rectangle from these two rows, then certainly the columns will be okay because every sequence of length 2 is also arithmetic. And I just need to find the intersection of all these intervals, so like all the points where they intersect. And I need to find just the maximum of all these rectangles. This is fairly simple. Because then, if it has to have an arithmetic progression both in the first and in the second row, so I just find all the intersections of these arithmetic progressions in the rows and in the columns, and I take the maximum. So these are just...
Not necessarily in consecutive circles, right? Because in that case, well, in that case, go to the right.
Yes.
And the line that is in the middle of those two
Yes.
doesn't have, like, that is both arithmetic progression. The red and the green one on the top.
Yes.
So you should be careful with that.
Yes. Okay, yes, you're right. Yes, so you should be careful. Okay, so this is, so you have to, okay, you're right. I wanted just to say something that these are special cases and not get into details, and I got into details, and this is my error. So these are special cases, you have to just consider them in a careful way. And finally, the most interesting case is when both W and H are at least 3. So we know that this rectangle that we are looking for, so let this be the, alright, so let this be the grid that we have in the beginning, and assume that this is the rectangle that we are looking for. And what do we actually do here is, I can see that, let us take this element. So this is like the adjacent element of the corner of the rectangle that we are looking for. And consider this 3 by 3 square. This is a 3 by 3 square. And if this rectangle is arithmetic, then this square is arithmetic. So like, this is an arithmetic progression, this is an arithmetic progression, and the same in columns. Not sure. If I take a subrectangle of an arithmetic rectangle, I get an arithmetic rectangle. But it turns out that it goes also the other way. So, if I take all the elements inside the arithmetic rectangle, so I don't care about the elements on the borders, I only care about the elements inside, like strictly inside the rectangle. If for each of them, the 3 by 3 square that contains it is arithmetic, then the whole sum is arithmetic. Because if you have one guy and this square is arithmetic, and then this for this guy, so maybe draw it in another color. And for this guy, the square is arithmetic. No, so the figure is so this is arithmetic, and then for this guy, this square is arithmetic. Then what it means? So here we have an arithmetic progression, and since here is the arithmetic progression with the same step, then all this stuff has an arithmetic progression with this step. Same here, same here. So these two just glue together into a 4 by 3 arithmetic rectangle. So this means that if I have a rectangle and I take put into circles all elements which are in the middle of a 3 by 3 arithmetic square, then this smaller rectangle implies the existence of this larger rectangle. So the whole problem is the following. We just take the initial grid, we draw circles around elements which are in the middle of a 3 by 3 square, and we want to find the largest rectangle that contains only these 10 circle elements. And the largest such rectangle, if I just like, no, but it's not the largest one, so I need to find all the So it's not a complete reduction actually. I don't know, I somehow get confused with this problem. So it's not a complete reduction. So I have a correspondence. If I have a W minus 2 times H minus 2 rectangle composed of encircled elements, then this corresponds to W by H rectangle, arithmetic rectangle. This is how it works. So if I find any such rectangle, then this implies such a pretty large arithmetic rectangle. So I just need to find, well, it is not true, it's not necessarily true that if I find a rectangle of this form with the largest area, and I perform this operation, I also can get the rectangle with the largest area. However, the algorithm, the standard n times linear time algorithm for solving this problem that I won't be explaining because most of you recall this problem. So this standard algorithm actually considers all the maximal arithmetic rectangles, all the maximal rectangles containing only one, so all the maximal one rectangles. So from these maximal rectangles, we try to enlarge each of them just by one in both dimensions, and then we pick the largest one from here. So it's not a complete reduction. However, you have to just take all the maximal rectangles of this form and just try to enlarge each of them by one in each dimension and just pick the right position. Strange. So confused with this problem. More or less clear? More or less. Well, here you could also, I'm not sure if the teams that solve this problem use this reduction or something else.
We did the case W equals 2 or H equals 2. We did this for every line equal to 2. We also had the information of arithmetic sequences in the rows, in the columns. So for each pair of line, adjacent lines, you have like the progression goes up like this. So you have some kind of histogram.
Yes.
And you can find the rectangle of maximal area in the histogram O n using this tag.
So like you actually didn't perform the actual reduction, but you like created an algorithm that's similar to this one.
Yeah.
Okay, I see.
We found out that we have a lot of lines that are direct progressions. And the first problem was always, if the reason between all the lines is also a progression, then the whole rectangle is. Then we get a histogram.
So this was like some combinatorial observation that if a number of columns if all the columns form arithmetic progressions and 2 rows form arithmetic progressions, then actually the whole rectangle forms.
Actually, only the first row. And the progression in between all the rows makes another progression.
Has to be.
Then
Okay. So this was just like some properties of arithmetic rectangles that actually boil down to the same solution as the basic problem, but just with no explicit reduction. I wanted just to show a very neat reduction for this problem, and I actually didn't succeed because it's not such a neat reduction. Still, you can just mimic the very But as far as this we are considered, the implementation of this solution is not really that nice. Requires several cases, considering several cases, and you can, like, it's very error prone. Okay, so after this problem, which was actually much more, like, it was not that elegant and it required some coding, there's this one problem that has quite a neat solution, but it was also not really popular. It was the problem of cave. I'm actually not also here again not sure why, for instance, you prefer the problem about ants, which is much more nasty to implement, over this problem of cave. Maybe there's one in the problem of cave. There is one combinatorial observation that you have to perform, and then you have just a small amount of number theory. Just a few words about cave. Just before I proceed to the cave, I have one thing from Fabio. There are two teams that Fabio would like to talk to. One is ICMC USP. It's something like that. I don't know if there are members of the team here. Yes, so if you could stay after today's contest just near the laboratories, then Fabio would like to talk to you. And the second one is Paul IUSP. Yes? Team here? POLIUSP. Okay, so also if you could just stay near the labs after the presentation, so that Fabio will talk to you. Okay, so this was just one quick announcement. And then a few words about the problem of cave. Maybe let's just do it a bit briefly. I don't want to stay on this problem for too long. Because the most important one probably is this IQ problem. So in the cave problem we have a tree. So just briefly, we have a tree and we want to divide it into subtrees. Each subtree of size k of the same size. And we want to know for what values of k we can divide this tree into such subtrees. So we have tree of n nodes for what k values of k. One can divide the tree into n divided by k subtrees, each of size k. So the main observation, I'll just go through two observations. The main observation is that we consider edges such that the sizes of both subtrees that are located to the left and to the right of the edge are all multiples of the parameter k. So first of all, assume that you would like to have a solution that just for a given k checks if this division of the tree is possible. Yeah, so just how to check if k is correct. How do you actually do it? You consider an edge to be like k nice if these subtrees located at both ends of an edge have both the sizes that are multiples of k. So ak and k. And the observation is that k is good if and only if there are n divided by k minus 1 k nice edges. And the proof of this observation is quite straightforward. What we do is, first of all, if there is a solution, so we have to choose the equivalence, prove the equivalence here. So if there is a solution, so if the tree can be somehow divided into subtrees, each of size k, then the edges that delimit the subtrees are exactly the k nice edges, because like each of them has a multiple of k on the left side and a multiple of k on the right side. And on the other hand, so this is just the proof from left to right, and from right to left if you want to prove. So if there are n divided by k minus 1 k nice edges, then I just remove all of them. And I see that what remains is just the decomposition that I was looking for. Because removing such an edge always leaves a number of trees, each of which has size which is a multiple of k, and none is empty. So if after I remove n divided by k minus 1 such edges, I get a tree, I get just all the subtrees with that subscale. So this is actually quite a simple observation. So from here we have one straightforward solution which is still not enough, but it's close to a good solution. You could just try, because k is obviously a divisor of n, so you could just try all divisors of n. For each of them, I would like to just traverse the whole tree. It's very simple to compute the sizes of both subtrees at the ends of an edge, and just check for each edge if it is k nice and use this observation. So by using this observation and checking all the divisors of n, I have a solution that runs in n times d of n. Just all the divisors of n, and for each of them just go through the tree. It is still not very big because the number of divisors of n is, for n at most 1 million, is not that large. However, still the solution is not enough. What you have to do is to actually consider all the values of k at the same time. And for this, to get a better solution, you actually consider every edge, and we would like to know for what values of k this edge is k nice. So if I have an edge, then I can take the left subtree and the right subtree. Assume that the size of the left subtree is x and the right is n minus x. If I remove this edge, so then I know that for this edge is k nice for all k that divide the GCD, greatest common divisor, of x and n minus x. This is k nice for all such values. Well, certainly true. So what I do as I compute the GCD of such value, well, first of all, I do some simple pre-computation on tree so that I can compute the x and n minus x values instantly, and then I compute the GCD for such GCD for each edge. And after doing this, I just can mark in some area, because note that GCD of x and n minus x has to be a divisor of n. Why is that? You know how to apply Euclid's algorithm to compute GCD, and one of the properties in Euclid's algorithm is that GCD of x and n minus x equals GCD of x and n, because I can just add the first component parameter to the second one. So this is the divisor of n, and I just increase. So for such an edge, I just have a table of size n, and for GCD x and n minus x, I just increase this value by 1. So first of all, I do this for all edges. I increase it by 1, and then I would like to propagate this information. So now I just increase it by 1 for the largest divisor, and then I would like to propagate this information for all the divisors of this number. Yes, because I know that this array T, I would like it like in the end, T of I would be the number of I nice edges. Like our goal is to have T of I for I, which is a divisor of n, is the number of I nice edges. what I would like to have. So first of all, I just increased such values, and then I need to so now I go from right to left. So then after this step, so this is step number 1. As and in number 2, I take all i's from n down to 1. If I is a divisor of n, then I want to take all divisors of I and increase the value of tk by well, this will be not a t, but okay, maybe I need a different array. So first I will have an array t prime, and then so I will just store in t prime these values from GCDs from ranges, and then I have tk is tk plus t prime of I. This is what we actually do here. So here I consider all the divisors of such a divisor. If E is a divisor of n, I consider all its divisors, and I increase the array value of all divisors of I. And then T of I is just what I was looking for, and then I just need to find that for each divisor whether this observation holds, and if so, I just output the divisor. The only question that remains is the complexity of this solution, because I take a divisor, a k that is a divisor of I, and so for each of the divisors of n, I take all of its divisors. So the complexity is the sum for all I that are divisors of n well, I can even write I, because I need to find all the divisors of I, and I can do it in square root of I time, but I can also do it like completely brute force in O of I time. And it turns out that this is n log of n. Just a fact from number. So just to summarize the solution, I just wanted to be quite brief in this solution, because I'd like afterwards just to proceed to the very main topic of today's talk. So just for each edge I compute x and n minus x, I compute this GCD, I increment the value of the array t prime for this GCD, and then I want to propagate this information for all the divisors of this value, and then I just do it in a single loop in which I consider all the divisors of I. And that's probably so I guess that we could somehow continue with like analyzing all the remaining problems. However, I guess it is better right now to proceed to the IQ problem that I really wanted to tell you something more about today, and then if we have some spare time, we can get back to the analysis of the problems. However, we will, it's not sure whether we will be able to continue this afterwards. So just the IQ problem, which I just wanted to tell you more about it, because I think that the techniques that are used in it might be more relevant to like some ACM, ICPC style contests, some more finals contests than most of the other problems. So it's, I consider even more important to talk about. I hope you don't mind about the choice of today's. So, what is the IQ problem, first of all, here? What are we considering here? So we have n students of maths and n students of computer science. And math students and n computer science students. And each of those students has an IQ. Well, everyone has an IQ. Here we know the IQs of all these students. So these are, I don't know. There is no denotation for it in the problem statement. So let's just, I don't know, xi with the math student IQ and yi with the computer science students IQ. And I would like to find pick a subset of math students and a subset of computer science students that has the largest total IQ. So I want to pick just subset of xi's and yi's with maximum total IQ. Well, if this was the problem, it would be totally simple. I would just take all the students. However, I have some relations that some people know each other, or some people like each other, some people know each other. So I have a set of pairs of the form AI and V. Okay, maybe this does not use the notation from the problem statement. So I have just several pairs of the form ij, which means that I, math student, and j, computer science student, know each other. So I have a set of pairs. And I would like to find such a subset so that each pair of students know each other. I am looking for a subset of students such that every pair know each other. With an additional assumption that all math students know each other and all computer science students know each other. All math students and all computer science students know each other. Okay, so I wrote to you this whole story because I was also not sure if everyone of you managed to read through this problem statement. However, well, after just brief reading of such a story, we all know what is this problem about. We are given a bipartite graph in which here are math students and here are computer science students. We have a set of edges in this graph. Each of those guys is assigned a number x1, x2, x3, and x4. Here is one, y1, y2, y3, y4, y5. And what I am looking for, maybe to have a non-trivial result. So for instance, if I draw it like 1 by 5, x3, y1, yeah, maybe like this. I'm looking for a subset of this graph such that it forms a bipartite clique. So all the elements to the left are connected to all the elements on the right, and i's are this the maximum possible. This is what we are looking for this problem. So if the problem is about some bipartite graph and I want to do something with this graph, it is like not sure, but it is almost sure that it will have something in common with matchings, with maximum flow problems, and with similar stuff. And it will have something in common with that, but it's not totally clear what it has in common here. What is actually the main idea in the solution? And that is why it would be a very nice idea just to go through all the weapons that we have. And for each of those weapons, just try to give several nice. Maybe let's just start with this. So, what weapons do we have when we want to tackle problems with matchings, with maximum flow problem, and so on? Just to get briefly through them, and I would like to just introduce or remind the major techniques that we need to be aware of. And during the introduction of these techniques, we'll actually get to the solution of this problem. So, what are our weapons? We have, first of all, when we have a bipartite graph, we can find the maximum matching. The maximum, or maybe the maximal cardinality matching. So the matching which contains the maximum number of edges, just to make sure everyone knows what is a matching in a bipartite graph, more or less. Yes, okay, so this is great. We just pick a set of edges that's known, two of them are adjacent. And so for this problem we have a solution. First of all, the basic algorithm has time complexity, the number of vertices times the number of edges. This is just by simple augmenting, by alternating paths. And just find the augmenting paths until I find the maximum matching. And one can also have an algorithm where it's in this time complexity. This is Edmond's, Hopcroft. Yes, this was Hopcroft algorithm. And it's good to know that these are these algorithms. I won't be getting into details about what algorithms are using these as black boxes. If you want to find out anything more about algorithms for maximum matching, maximum flow, and so on, it is good to just go to Topcoder tutorial, for instance. Tutorial. There are a few parts of this tutorial about matchings, flows, and so on. All these algorithms are explained. Okay, so this is weapon number one, and let's just stay for a while on this weapon. There are also several applications of maximal cardinality matchings, which are somehow also quite well known, and very often you want to try to use them. So there is this nice, we'll be getting into this nice finish here. So what does it say? So if I have the maximum matching, that's just the same size as the size of the smallest vertex cover of the graph. What is a vertex cover? The vertex cover is we want to pick a set of vertices such that each edge is adjacent to at least one of those vertices. So if I have a bipartite graph, maybe like this, then I can maybe this kind of graph. I can select these vertices as the vertices of the vertex cover, and then every edge is covered at least one end by the vertex from this vertex cover. And it is quite natural that well, one of these because these are two inequalities actually. One of these inequalities is actually trivial. So if I have the maximum matching, then there is no other way to cover all the edges of this matching than selecting at least one vertex of these endpoints of the matching. So then I know that the smallest vertex covered is actually not greater than so it is at least, so the maximum matching is a lower bound for the size of the smallest vertex covered. However, you could have the vertex covered could potentially be greater. However, one can just simply show that it is not really greater by just a very simple algorithm that you take all the nodes that are leaves, so the nodes that are just endpoints of just a single edge. We say that these nodes won't be taken into consideration in the vertex cover. We take their neighbors. We say that these nodes will be in the vertex cover. Then we take the neighbors of these and we say that these won't be vertex cover, won't be contained in the vertex cover because they don't have to, and so on. And we continue this process until we obtain the vertex cover. And it is quite easy to prove that if this way one would obtain something that is not a vertex cover, then the graph would contain an out and in graph. So you can just show that these two are equal. But this is not all. There are more things one could consider. For instance, there is this independent set. So the independent set, I have the largest independent set. And the independent set is a set of vertices so that no two of them are contained, no two of them are endpoints of an edge. So no two of them are connected to an edge. So here is just vertices that cover all edges. And here is vertices, no pair of which is connected by an edge. An edge. And actually, here we don't have that these two are equal, but we have that the sum of the size of the smallest vertex cover plus the size of the largest independent set is just equal to the size of the set of nodes of the bipartite graph. And here it is very important to understand why is this true. Because you just take, if you take the if you take a vertex cover in the graph and just remove all these vertices and look at what remains. So I take all the other vertices of the graph. Then what remains is a set of vertices so that no two of them are connected with an edge, because if one of them would be connected with an edge, then this edge should have been covered by at least, would need to be covered by at least one node in this vertex cover, but it's not. It is not covered because we removed the vertex cover, so this is a contradiction. So this means that starting from a vertex, if we remove, maybe let's write it like this, if we take the set of nodes and we remove vertex cover, any vertex cover, we get an independent set. So to obtain the maximum independent set, I remove the smallest vertex cover. So that's how it works. Just again, if I have a vertex cover and I remove it, then any two nodes in the resulting, there cannot be an edge because then this edge will be covered by at least one of these two and it will be part of the vertex cover. Okay, so let's just come back for a moment. So we have now several tools that we know. And let's just come back for a moment to the original problem that we are considering, the IQ problem. What do we want to find here? In the IQ problem, we want to find the largest bipartite clique in the graph. Here, the largest means with the largest sum of IQs. However, we can just for a moment assume that all the IQs are 1. So just assume, let's come back to this original IQ problem, and assume that all xi's are 1, all yj's are 1. But all the IQs are just 1. So we are, in this case, we're looking for so the goal here is to find the largest bipartite group. The largest meaning with the largest number of nodes. And it turns out that this reduces to one of those things that we have already considered. How does it work? We take the complement of the graph. So let G be the original graph. And let G prime be the complement of this graph. So what it means, we don't take edges that were here and we introduce all the edges that were here. Yeah? So what is a bipartite? If I have a bipartite link in G, what is it in G prime? And this is an independent set. Exactly. So if I have a click in G equals independent set in G prime. So this is another thing that I can write here. Largest independent set equals largest bipartite click in graph complement. So this is another thing in the scheme that we can actually do. So this would actually solve the problem. Well, I didn't say how to actually, because the problem really requires how to recover this bipartite click that we are looking for. However, it's here not that important because we still cannot solve the problem because we make an assumption that it's totally not true in the problem state. We assume that a simplifying assumption, we make a simplifying assumption for these two points. Okay, so we have some insight into our IQ problem. Still, it is not yet the solution. But we know something more. This won't be necessary in the solution eventually. However, it's good to know that we can now proceed to other weapons. This weapon just gave us this insight. So the next weapon will be the maximum flow. What we have, so this was the first weapon. Now some other weapon, I guess that you all know the problem right now. Weapon number 2 is maximum flow. In the maximum flow problem, we have which of you know maximum flow problem? Something? Okay. And so just recalling, we have a graph. We can assume that it is a directed graph. Each of the so we assume a directed graph. We can assume for simplicity the integer capacities on edges, and we have some source node S and some node C, and we want to find the maximum. And there is a family of algorithms that can solve the problem. Well, the most commonly known is the Edmonds-Karp algorithm. And Edmonds-Karp algorithm has time complexity, the number of nodes times the number of edges squared, which seems totally ridiculous. On the other hand, you can also limit it by the number of edges times the resulting max flow, only in the integer case. And there's also a family of very efficient algorithms that work in time cube time that is a cube of the number of nodes. And these are somewhat like some algorithms like the Dini's algorithm, some variants of the Dini's algorithm, and some pushing label algorithms. There is a number of such algorithms. It is quite a good habit to have at least one of such algorithms implemented so that you can just, in a case you need it, you can have an efficient algorithm that just solves the problem. I guess that this top color tutorial also contains a list of such algorithms. So this is a very nice tool, this maximum flow problem. I want to find the maximum flow in the graph. And what is the most important property of this maximum? How will we be using this maximum flow algorithm? There is this one very important theorem that is actually used most commonly in the proof of the correctness of all these algorithms. However, it can be used to solve problems that look like you couldn't solve it. And this will be the tool of the mean cut max flow theorem. Maybe some of you have heard about this mean cut and max flow, yes? Mean cut, yes, okay. Yes. So this will be actually also necessary in our problem to solve. So this is mean cut max flow. And this theorem says that the mean cut is equal to max flow. So we can actually write it like this: mean cut equals max flow. Max flow is the maximum flow from the source node to the sink node. And what is the mean cut? I take the node S, I take the node T, and I want to divide the graph, so all the nodes of the graph, into two parts, so that you cannot get from the source to the sink. So the source has to be in one part and the sink has to be in the other part. And the size of the cut is the sum of capacities of these edges. Like that go from one set to the other set. And the minimum cut is the minimum size of such edges that we want to cut so that we cannot get from source to the sink. And so the theorem says that if you find the maximum flow, then it's exactly the size of the maximum flow is exactly the size of the minimum cut. So the sum of the capacities on the minimum. And how do we actually make use of this theorem? Maybe let's consider a toy problem where we can explain how can this be used. So there will be two toy problems. Which of them I should start? Maybe this one. No, but actually, maybe we can start with the easy one. Okay, so maybe let's start with this. I wanted to start with a more difficult one, but maybe we'll start with the easier one. This is a problem from from COI 2008. This is some Central European contest. And, but it's totally not the kind of Olympiads in informatics, I don't know why it was there. So we have a number of orders and a number of machines. So we have n orders and n machines, and each order has to be performed on a number of machines. Maybe I don't want to do it. Okay, sorry, I changed my mind. I prefer to do this second. So this will be the second one. Okay, just I want to choose the order of presenting problems so that it is more clear. So let us first start with the problem of travel agents. This is the less commonly known problem. So we have n clients that want to take part in an excursion. maximize the profit of excursion. And what we can do, we have two types of constraints. The first type of constraint is each client xi has gives us what is the value of the excursion for this client. How much he is willing to pay. And xi could be both positive and negative, meaning that if xi is at least 0, then the client pays xi, and if xi is less than 0, then we have to pay the client for him to want to go to our excursion. He really doesn't want to go there. We have to pay minus xi to the client. So we might not want to take such a client. We have to really pay the client to just go for our excursion. However, we might be forced to do that because the second type of constraint is that for each client I, there are these social requirements of the client I. There is a number of social requirements of the form Aij, Bij, which mean that for each Aij, it means that either, so if client I goes to the excursion, then either client Aij must also go, or we need to pay Bij to the client line. So this is the second. So the client I really wants his friends to go, but well, okay, if this friend doesn't go, then just pay me money. Maybe this is a bit strange, but this is the type of constraints, and we want to know what is the maximum profit that we can make out of organizing such an excursion. Well, possibly we might want not to organize the excursion after all if nobody wants to go there, and if all people require quite a lot of money to be paid to go there. And actually, this is just, you don't have really too much time to think about the problem. However, if you just try to think about this problem without using any tools or anything like that, and it's like, I don't know, a few hundred, you can say 500. If you try to think about this problem for some time, you might even try to make a conjecture that all this has to be NP complete. I don't know how to solve it, just no idea. And actually, this is a nice, if you see a problem that could be NP complete but has quite a lot of quite large bounds on the input size, you might just think, and if it is additionally a graph problem, this is a nice signal for you that this might be a problem for maximum flow. This is just like some kind of a way to get that, okay, this is something peculiar, I don't really know how to solve it, maybe we can try the maximum flow. And here, this will actually be the case. We will solve this problem by maximum flow, actually by the theorem of this mean cut and maximum. And normally, so we need to build a graph, we need to find the maximum flow, and from this maximum flow, we'd like to know what is the result, somehow. So we start, as usual, with the source and the sink. It is most often the case that we just have to add the source and the sink to the graph. And we have to create some nodes. Normally, the nodes correspond to some entities of the problem. The most important entity here are the clients. So certainly all the other nodes will be the clients. Nodes are clients. Like vertices are clients. And we have to connect somehow the vertices, the vertices, the source and and some vertices one to another. Well, one thing that is totally clear is we have connections from a client to such a pair of client and requirement. This totally looks like an edge in a graph, so let's just drop the edge and just check what happens. So I draw an edge from client I to every such client Ij, and the value of the capacity of the edge will be Vij. I draw all the edges for such social requirements. Next, I have to somehow connect the nodes to the source and to the city. So what other parameters do I have in the problem statement actually? I have only these xi's. And clearly there are two cases. One is the case that someone pays, and the other is the case when we have to pay to someone else. So we will connect, the first guys will connect to S, and the other guys will connect to T. So there will be these two sets, V plus and V minus. This will be the set of guys for which xi is at least 0, and this will be the set of guys for which xi is less than 0. And we will connect from S to, okay, so is it better, just here we have to take a guess. From where do we put edges to where? So we either can connect S to V pluses or S to V minuses. We take a guess that we take S to connect S to V pluses and V minuses to T, and here the weights will be xi, and here the weights, the capacities will be minus xi. So these are the nodes for V plus, and these on the other hand are the nodes on V minus. So this is V plus, and this is V minus. And now we just run the maximum flow algorithm and we are happy. But actually, let's try to consider what is this graph really about? What are we really looking at? What is happening here? So what we need to know is we would like to somehow make an interpretation of how do all the cuts in this graph look like. Because we want to use the mean cut max flow theorem, which just says that we don't care about max flow. We know that this mean cut max flow theorem just says that we can compute mean cut. So the only question is, what is mean cut in this graph? What does it correspond to actually? So let's consider the mean cut in this particular problem.
So this client has exactly one social request.
You can have even 0 social requests.
Okay.
Yeah, it can have a number of social requests. Number of social. Yeah, this is this J here, but I maybe didn't just articulate it well. So a client has a number of social requests. And so the question is, what is a cut in this graph? So if I have a cut, then I have S, and I have a number of nodes in this part, and I have T, and I have a number of nodes in this part. And here is the cut. Here are the two opposite sides, and here are some edges going. So I claim that this cut corresponds to these clients going to the expansion. They go, they don't go. But what is more, we are looking for that maximum profit of an excursion. But what we can find is mean cut. Mean, not max cut. Max cut is actually, the max cut problem is actually yeah, but still, we are looking for the mean cut and we want to find the maximum profit of an excursion. So this is often the case in such problems, that what we do is we subtract the value of the mean cut from the maximum possible achievable sum. So the maximum that we can get is the sum over of xi's for xi's in V plus. We cannot get more than that profit. Well, we assume that the social requirements are, well, this is actually clear that V and J are that easy. So we cannot get better than that. So I would like to prove that a cut, so mean cut in this graph corresponds to this m. So maybe m minus mean cut is the result. So if I subtract the mean cut from the maximum possibly achievable sum, then what we get is just the result. Okay, so this is the time to just take an interpretation of this problem. What kind of edges can we have here? Well, there are just three types of edges. From S to V plus, from between the nodes, and from V minus to G. So what happens if we have
There is no problem with the capacity right?
in the capacities not so they are?
That means they have to be. Because you are only having the XY that are in the class.
Nice work.
You are, for M, you are only adding up capacities that are in the class.
Yes.
And maybe capacity because they are very small and even some fragments that are.
Yes, but this is the maximum that we could possibly achieve. We cannot achieve it possibly. So this is the maximum that one would theoretically get. You cannot get better than that in the solution. There are some guys with negative, but it is better for us not to take them. So if there were no social requirements related from V plus to V minus, then we can just take all these guys and not take all the others. So we cannot get better than that. This is like the upper bound on the result. So now there are three types of edges that could be here. So let's just, what are these edges? Well, the first type of edge is, so here are the guys that we claim that go here. So first of all, you could have an edge from S to someone to V plus. One of these edges could be from S to someone to V plus. So let's just draw it maybe in black. So here is S, and here is some xi in some V in V plus. So this edge is in the cut. So I cut this edge, so this means this guy doesn't go. So in the weight of this edge is just xi. So by cutting this edge, I lose xi. Okay, this is exactly what I do. I don't take this guy, I lose xi because he's in V plus. Right. On the other hand, you could have here a guy that is in V minus and an edge to V. Here the value of the edge is minus xi, and this edge assume is undercut. I have just three options of these edges. Okay, so if this edge is undercut, this means that they go. I take V.
You have to satisfy all of the requirements?
Yes. Yes. Well, for all the requirements, I can either take this. Well, all the requirements like all the requirements as they are just formulated here. So if the client I goes, then either this or this. There are no other options. Yeah, but still, we haven't really got to the requirements. So the other option is that V is in V minus and he is in this part of the cut. So this means that we take V. And what does it mean? We have to pay this guy minus xi. And this edge is on the cut. Okay, so the cut will say how much do we lose compared to the upper bound, the maximum that we could possibly achieve. So here we lose this because of not taking V that is good for us, and here we lose because of taking a guy that we really don't want. And the only other type of edge is a social requirement. So from some V to some W, and here is some. Okay, so maybe let's just, here is I, here is Aij, and here is Bij. What does it mean? Okay, we take this guy I, we don't take this guy Aij, so from the social requirement, we have to pay this guy Bij. So if this is on the cut, this adds up to the maximum, to the cut that we currently have. So we assume, if I have a cut that I decide these guys to go, then I have then all the edges that are on the cut, so all the edges that go from left to right, the money that I lose due to this selection. I lose them, so in the best case I could get them, but I lose because of not taking guys from V plus, taking guys from V minus, and not satisfying social requirements. So I would like to lose as small amount of money as possible. So I want to take the minimum such cuts. If I take the minimum such cut, then I lose the smallest amount of money comparing to M. So this is this one. So the solution to the problem is the following: build this graph, find max flow, and since max flow equals min cut, I have the solution. Check. This is okay. So during this explanation, I really tried to tell you how do you actually have an intuition how to build this graph. Because after we have this graph, I can just prove it to you. I can just explain. One thing is that how do you actually build it, and this is how you actually build it. So maybe let's just do this order, this problem from COI 2008 that I wanted to do just in the very beginning, just to have an intuition that, okay, this way of solving such problems really works. And then afterwards we will get to the solution of the IP problem. And the very end. Okay, we have something. So we are getting to this, back to this problem from COI 2008. This is this problem, name of the problem's order. So we have again, we have n orders and n machines. And what parameters do we have? First of all, an order I has some money we get for completing this order. So we have AI money we get for completing it. And how can we complete orders? Well, each order has a number of machines that have to be used to complete. So again, for order I, we have a number of machines. So these machines are some VI1 up to VI. Okay. These are the machines that are like we have to use to complete the order. And each of these machines can either be bought or we can rent the machine. And for a machine, so we have two choices. For a machine I, we have CI is the cost of purchasing the machine. The cost to buy this machine. If I buy a machine, I can complete all the orders that require this machine. On the other hand, if I just don't really need this machine for too long, I cannot buy this machine but rent this machine. And here in this set of requirements, I also have the money required to rent this machine just to complete this very order. So we have, so maybe this will be DI and this will be CI1, CIKI. How much to pay to rent this machine? So if I decide to complete order I and I need the machine Bij, then I either can buy this machine, paying this amount of money, or I can rent this machine, paying this amount of money. And as usual, I want to get goal maximum profit. This is the goal. Cool. So, as you might guess, we might be going to min cut max flow, and now after looking at this problem for a moment, we see exactly how to build the graph. It is just written here. Yes, how to build the graph to this min cut, and then after we are able to build the graph, we can prove that this min cut is actually what we want. So, what do we have to have? A source, a sink. This is one thing. Then we need to have some vertices. What are the natural entities in this problem? Exactly. So we have orders and machines. So now we can easily deduce how will the edges look like. From a just AIs, money for completing this order. Well, we don't really have anything more in this problem, so just drop it. So these are AIs. On the other hand, from orders to machines, well, we have here are just the edges from the machines with these weights on edges. Okay, just put them. Don't think too much, just put them. So from order I, we have BI1, BI2, and the weights will be CI1, CI2. And again, from the machines to the, of course, this will be the DIs. This will be the and again, as we are looking for maximum profit and we get mean cut, what we actually have is that M, again, the upper bound of the result. The natural upper bound, here there are no negative numbers here, so the natural upper bound is just sum of AIs. This is like, we cannot get more than that. This is the upper bound of the result. So I want to prove that the result is M minus cut in this graph. So, how do I actually do it? Previously, we have interpreted a mean cut as so that, like we said, that the cut, any cut is like implies the number, the particular players that are present in the cut. Here we can do a different type of analysis. There is also a second type of analysis that one will do, because here the structure of the paths in this graph is really simple. All the paths have length 3. Like all the paths from S to T have length 3. So what do we actually do? We take a path. So we imagine a cut in this graph. Imagine a cut. It looks like whatever. Yeah. This is a cut. These guys go here, and all the other guys go. This is a kind of a cut. And I know that this cut cuts each path from S to T, and all these paths are length 3. And I want to give an interpretation of cutting such a path. So a path from S to T is, first I have some AI, I get to the node I, which is order. Then I get to a machine. And here is AI, here is Ij, and this is node Bij, and here I get to T, and here is Bij, then it will be D of Bij. So this is F. And I know that this cut that I depicted here has to cut this path, because it's cut. It has to. And how to interpret this cut? If we cut here, then we do what we do. We don't complete the order, we just don't care about the order. So here, just don't complete the order. Okay, if we cut here, what does it do? I didn't hear. Yeah, we went to the machine because we decide, okay, so I complete this order. So if this order is in the left part of the cut, so if there is no cut here, then I know that I have to complete the order. So to complete this order, I may decide to rent the machine. I rent the machine. And finally, I could cut here. So if I decide not to cut here, this means I complete the order. I don't rent the machine, so I have to buy the machine. And exactly the cost here. If I don't complete this order, then I have minus AI to the total sum because I lose the money for not completing this order. If I decide to rent the machine, I lose Bij because of having to rent the machine. I pay this much of money to rent the machine. And if I cut here, I pay D Bij for buying this is the cut that we are, each cut has to cut each such path of length 3. Then for each path, I have to make at least one of these decisions, so this means that actually the order will be completed as expected. Well, one can have more edges cut here, but it doesn't really, if we decide not to complete the order and also pay for renting the machine, then we are just crazy. So. you don't want to. Okay, so this shows a correspondence between a cut and how it corresponds to completing the orders related to the problem. So this is how we just prove it. So note that I recall this competition from, it was for high school students actually, but quite good competitors were there. And I guess that none of the competitors just came up with the solution, and the solution is just almost written in the problem statement. Just throw this graph as is just said here, run maximum flow, and think how can you get the result. So this is the way how you, at least how I look at such problems. It's the way how we can try to solve such problems to somehow eliminate this stuff. Okay, and now,
One question.
yes.
What if the orders are not partitionable? You cannot partition the orders. I mean, the orders are tasks, right?
Yes.
This task is, can be partitioned or not.
No.
So for one order, you just use run machine.
No, for an order you can have a number of machines.
Okay. So what if you have to use that one machine for one order?
So a different problem. Well, certainly the solution works, but maybe you can have a simpler solution. I don't know. I just cannot tell you off the top of my head, so I won't try. Okay. So now let's get to the IQ problem. Right? If we all remember what was this IQ problem about, right? Well, this is not the only way to solve the IQ problem. There are other ways to come up with the solution to the IQ problem, but I think this is the easiest to do. So, recall the prior analysis that we made. We want to find a bipartite leak in a bipartite graph with the maximum sum of weights. So I have to find the heaviest bipartite leak. This was the problem. And as we noted, this is in G and in G prime. Sorry, this is in G. In G prime, this was to find the heaviest independent set. Okay. Because here I just complement the graph, and all the arguments that were with the non-weighted case just follow here, apply here. And this is exactly this. I take all the other nodes, not from the independent set. In G prime, I want to find the lightest vertex cover. Yeah, so I take the vertex cover with the minimum total weight. So as we go along this path, we can only concentrate on this problem. After some analysis, it is better to try to solve a problem that is well known, not a problem that are more exotic. So I want to find the lightest vertex. If I find, okay, so this is not equals actually, yeah. So this is sum of this equals. Yeah, to have a real equation, I need to sum up all the weights, sum all xi, sum all yi's, and subtract the lightest vertex cover, and this will be the heaviest independent set. So this is just a series of reductions. How do we get to the problem of I want to find the cheapest, the lightest vertex cover. Let's call it cheapest. So I want to cover all the edges of the graph, and I pay for taking a node by just paying this amount of money that I pay the amount of money that is equal to xi or yj. Okay, so what we can do? We can draw a bipartite graph as it is set here. Add a source, add a sink, add some edges, put use maximum flow and check what happens. So let's do it. Let's use the same strategy that worked for 2 previous structures. Just do it. But there will be one catch in this. So, I have these xi's, x1 up to xn. I have these yi's, y1 up to yn. I add a source, I add a sink, why not? So let's start drawing edges. What edges do we have here? Well, this is quite obvious. There are only numbers xi's here, so let's just put the weights xi. x1 up to xn. Here, the same. y1 up to yn. Right? No better choice than that. Now we are getting closer to some problem, okay? We know what edges to draw here because we know that if x1, xi likes yj, then we add an edge from xi to yj. There's a number of edges that just like each other. But what is the capacity? We don't have it. Normally we just use all the numbers that appear in the problems. Like, not just put them here. Here we don't have it. So we have to come up with a number. Some simple number. 0, infinity. Okay, let's put infinity here. There are several simple choices that we could make. 0 makes no sense because then the cut is just cut all these guys and don't care if you pay 0. You could put 1, sometimes you put 1 in such problems, but here not. Because you don't really see how this number 1 really corresponds to these units. Like unit 1 has no correspondence to these units. It just makes no sense. You can put infinity and check what happens. So let's try to apply minimum cut in this graph. What's the minimum cut here? Well, here the interpretation will be even simpler because you don't want a cut here. You don't, yeah, because you will pay 2. Don't want to cut here. So you want to cut either here or here. And what is the property of this cut? How do the puffs look like here? The puffs are extremely simple. As xi to the guy xi, here we have infinity to get the guy yj, and here we have yj to t. And since you don't want to cut here, no, you can cut either here or here. Well, you have to cut either here or here. At least one of these two. Maybe this one is drawing another color. So what does this mean? If I cut it like that, I have to cut either here or here. Anyone sees an interpretation of that?
Kind of sacrificing the line and not putting in blue.
Yes, but I am. Recall that we are thinking about the cheapest vertex cover problem. For each edge, I need to cut here or here. This means I have to choose at least one of these 2 vertices and put it to the vertex cover. Because each edge has to be covered. So I cover it by either picking this guy or by picking this guy. So let's cutting here means I take xi to the solution, and cutting here means I take yj to the solution. And each edge, since it has an infinite capacity that I don't want to have here, each edge has to be covered either here or here. So here, simply, mean cut is just the result. You don't have to subtract anything, because I want to find the cheapest vertex cover. So this is just the cheapest vertex cover. Nothing less, nothing more. When I decide to cut here, this means I just xi in the vertex cover. And if I decide to cut here, okay, this means yj in the vertex cover. So apart from solving this problem, you also know how to find the lightest vertex cover using just maximum flow power. And this is exactly the solution to the highway problem. But as we see, we presented 3 other problems that like used this maximum flow technique. And so this is a very nice one actually to discuss. And actually there is, so we have concluded the description of this problem about IQ. And there is just, we presented 2 weapons up to now. We just have to be aware that there is weapon number 3. Weapon number 3 is you want to take weighted maximum flow. So you want to take the weighted maximum flow problem, in which you have, apart from the capacities, you have weights in the edges, and you either will find a weighted, so the cheapest or the most expensive matching in the bipartite graph, or in the general setting you want to find the maximum flow where for each unit of capacity that you push on an edge, you pay a fixed amount of money that is given on the weight of the edge. So each edge, so edge has capacity and like the weight pushing the unit of capacity to the edge, and you just need to know that there is an algorithm based on potential functions. A potential method yields an algorithm that is with time complexity, which is the number of the cube of the number of vertices. Yes. You could also spend, I guess this will be, alternatively you could use some Bellman-Ford algorithm to get something like this via Bellman-Ford. I also guess that all these algorithms are on top of the tutorial, so if you never encountered them, it is good to do it sooner than later.
None of them depends on the weights of factors of the density.
Yes?
None of them
Ah,
as the density depend on the capacity or the weights. That's what I'm saying.
okay. So what's the question?
And the complexities, I see they don't depend on the capacity of the weights.
I think it's okay. I would have to rethink it, but I guess there is no hidden catch, as I recall it. And this weapon number 3 is actually a weapon that is mostly used for a given type of objects. You can shoot at given type of objects. You just have to somehow identify that a problem is like of this kind. I recall that there was a problem. It was one of the ICPC finals. It was several years ago. This could have been 2005, I guess. There was one problem about some pieces moving on the chessboard, and it was just, some people just tried to solve it by hand, and it was just the problem, just use it, just use the tool. So it is nice to have the tool, because from time to time, it just turns out that this tool can be used. So just check. This was MICPC finals. I will maybe try to solve it, try to send you a link on the email that will just with all the other information that I have promised to send you. It was 2000, would have been 2005. I think so. Yeah, so this is good to know that there is this way. And just as some last remarks about today's competition and some advice that I promised you about participating in the competition. So today will be the last team contest, and tomorrow will be some individual round. So today is the last chance of participating in teams. And there's also one nice thing from this contest, because I managed to bring from Poland a few of these books, 5 books looking for a challenge books. And the 5 top teams today will receive such a book. So there are some problem descriptions from Poland and some other authors. Well, we might at some point have more of these books, but it's not so easy to bring these to Brazil. So I think one book per team is better, because then I will put more teams because then we some of you might have received such books from your coaches, because we distributed them during the last night, but then we have the books, so it is try to solve problems. And just a few pieces of advice from how do we participate in, from some pieces of advice of how the teams participate as in competitions in Warsaw. Well, one thing I just, yesterday I tried to look, have you participate in the contest? One thing that was a bit surprising for me is that I already asked the organizers, is the printing enabled? Because nobody is printing anything. It was quite surprising for me that no team was printing any code. And actually, I don't know what is the way, because the one question is, assume that you solve a problem, you are trying to solve a problem, you submit it, you get the wrong answer. The question is, what happens now? Well, you could just go home, but it's not the best option. Not the best choice if you didn't succeed. So what we do quite often as our teams do is just it doesn't really count for very simple problems where you can just afford 2 more minutes just to debug the code and have it accepted. It is very simple. But if it is not simple, you usually just print the code and get sick with the code and just try to read it. Quite often you get many more errors from that than just looking at the monitor or trying to test. You might just put a few random test cases, but if there are no test cases, a few small random test cases where the problem is failed, you can just print it and just start reading. Okay, and as I'm reading it, I often find some errors in the code. And it is a nice advice just read the whole code as I start reading. Not just, oh, I find an error, so okay, so just give me the computer, I'll correct this error code. Doesn't, and syntax. It's maybe better just to read through whole the code and just find all the errors that you can find. Okay, and you corrected all the errors, you submitted, wrong answer. That's a sad moment. Well, you can, at this point you might start thinking maybe the algorithm is incorrect, not the implementation. And but if you think that the algorithm is correct and there's something wrong with the implementation, you have no idea what is that. You can take your teammate with you and just start. You have this printed code and you just read the line by line, like saying this guy, what is really happening? So just explaining the code. What is the purpose of this? Do you want this other person to find a bug in your code? No. Because the other person will not necessarily understand everything that you tell. You, who is explaining, will find the bug during the explanation of the code. That's what happened actually today. I was describing the solution of the arithmetic rectangle. I already managed to write a small popular article in Poland about that. I didn't notice some small errors that were in the article that I just, today there was some confusion about these rectangles with tools, whatever. I didn't really notice that even by writing an article about it, but I only noticed that when explaining to the algorithm. So this is only the moment where I note, oh, there's a problem, oops. Yeah, and this is similar stuff happened yesterday. So during such an explanation, you just quite often can really find a bug, well, you could also try to explain this problem to a wall, but you might not be able to imagine that the wall is this. So if you are able to explain a wall that is cheaper, but it's difficult to do. And okay, so you explain the code, you found all the errors, you submit the program and programs. And this is the last step, and okay, so this is also a good moment to just go home. But you might try at least one more thing. There are some very tricky problems. I'm just explaining to you our team that once won the World Finals and they participated the next year, and they actually the next year didn't get a medal. And it was a big disappointment for our university. What happened actually? And the problem is that they got stuck on a problem that was easy, or easy plus, something between easy and medium. And one guy just did all the stuff that I told you. First read the code, then explained it to his friends. And what do you do after this moment? You don't want to give up an easy problem. You see everyone is having it, and you don't see what is the problem. There is this third contestant. The teams consist of 3 people. And you can try to give this problem to this third guy. And what is the main, the worst thing that you could do at this moment? Because this guy maybe doesn't really know too much about the problem. You have explained it to your other fellow contestant. The worst thing you can do is to tell this guy what is this problem about. Because when telling this, if there is some conceptual error that you made during the solution, you just tell the guy the error. And this is the reason why our team failed at that time. They followed the whole strategy, but at the last moment, they give him the third contestant the problem, they just told him what is the problem about. It doesn't really take too much, it takes 5 minutes to read the problem statement. And that other guy unfortunately got the same conceptual error because they just told him that. and they didn't solve the problem for the whole contest. And like having solved many other problems, they were like without an easy problem, it is very difficult to get a medal there. So the team that lost the year before just won the finals. So this is actually, so then you can just give the problem to the third guy, and just solve it, just from scratch. Just read the problem, try to solve it. If it is easy, an easy problem, this guy should be able to solve it. So then, this might be the last way to go. It's not very common that all these steps like appear, but you might just encounter this. And the second advice that I would like to tell you is about the end of the contest. Well, there's this 5th hour of the contest. You have, most often you don't really assume that you will like finish all the problems in time, because nobody really finishes all the problems in 5 hours, most of them. So at this moment you have to somehow decide which problems you really want to try to solve. And it is often the case that each of the teammates just is trying to solve one of the problems at the same time. So that it is almost improbable that all of these guys succeed. So sometimes you have to just select one or two of these problems that you really want to try to solve. It is also often the case that you have just finished your last summit just before the 5th hour, you submit and you have accepted. And now you see several difficult problems, and all the people in the team are free right now. They are not solving anything at this moment. So you can try to use the whole team trying to solve the problem. So first, two people can discuss the solution. It is quite often the case that when two people that think in a really different way come up with the solution by discussing just way faster than the single person. And then they come up with the solution, and then what can happen? One person is writing the code, and the other is just staring at his monitor and just looking what he's coding. And if he doesn't understand something or just says that you might have a bug here, then this guy just can you can just have some bug in this is just +1, -1. And then it turns out that at least what our experience says is that most often code that is produced like that, the one person is coding and the other person just staring at the monitor and just punching him. It is most often either 100% correct just after the first writing or just one small error. So it is quite often the case, and this is the last hour, you don't have too much time for debugging. And then this might be a good technique. I'm not sure, I'm just telling you our experience. Might not be the case that this is the best strategy for your team. There's no best strategy like ultimate best strategy, just some things from our perspective. So this could be, and the third person in the team could try to design some test data for the problem just in case. And it is always important, if you try to generate some input data, to try to imagine or just to write down what should be the output. Because often, okay, you run the program with this input, the output looks correct, submit, and it doesn't looks correct. But if you thought just beforehand, you could see that, okay, so this is not this output, but looks correct. So this is, and there is also one thing about rank list. There is this rank list during the competition, and I noticed, I guess, that some of you just keep looking at the rank list and just try, maybe try to just learn it by heart or whatever. But the one thing is, by looking at the rank list, you don't get new problems accepted by just looking at it. So it is quite often good case we normally have one captain in the team, but you might have all the teammates might be captains. So we have this captain of the team, and he just looks at the rank list, sees which you have to follow the rank list to see which problems are actually being solved right now, and then you don't have to really look at it too much. You will have plenty of time to look at the rank list after the contest actually. So you don't have to do it too much during the competition. Because it just takes time. Just look, interesting, they solved this problem, they solved this problem. No, just look which problems were solved, try to solve them, and just don't really care too much maybe about the rank list. And just very lastly, before we get to lunch, a very simple one. There are often problems, it is not always the case here because I'm just giving you problems from different sources. Just trying to choose problems that are best for ICPC style. Then there are multiple test data in a problem. Then there are multiple test cases. First you read the number of test cases, and then you just read the test cases. And you have some sample input in the problem statement. You have, for instance, 2 test cases, here is 1 test case, and here is this. How to make something that is very cheap and might be very helpful. A common bug in such a code is that you don't clear some array. You don't put zeros in an array or whatever. You don't zero any variables. So what you can do is you type the sample test case from the problem statement, Then you write here 4, and you copy paste this stuff here. If the results here and here don't match, you have a bug. And it is even more helpful if there's just one test case here. Then just copy it, just the second one, and it happens from time to time that you say, wow, these outputs are different, but the test case is the same, there's something wrong here. So this might be a very cheap way of finding the bugs just before submitting the program and not after getting out of it. Okay, so thank you for today and good luck with the